You must have remembered that yesterday we have discussed about the critical section problem. In the critical section problem, we have discussed that there is the critical section is the section of code which modifies the shared data, and we must ensure that no other than one process should be there in the critical section. So there more than one process should not be present in the critical section. To ensure that one process has to be in the critical section, we have a entry section before the critical section and an exit section after the critical section. So some code has to be executed in the entry section and some code has to be executed in the exit section. The rest of the code are called the reminder section. And we have also discussed that whatever the solution will make for a critical section problem, the solution should have three properties. Whatever the solution you propose for a critical section problem, solving a critical section problem, that solution should have three properties. What are those properties? Mutual exclusion, progress, and bounded waiting. We have already discussed those. Mutual exclusion ensures that no other processes can be, if process PI is executing in its critical section, no other process can be executing in their critical section. That means at a particular time, one process must be present, may be present. This is mutual exclusion, right? The progress says that if no process is executing in its critical section, then there exists some process that wish to enter into the critical section. Then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. So if a particular process has finished its execution in its critical section and it has finished, now many processes might be waiting outside to get in the critical section. So there must be the waiting cannot be postponed indefinitely. They must get a chance. And the third one is the bounded waiting. It ensures that whenever a process is admitted and the time it is being granted to enter to the critical section, there must be a fixed number of, there is a bound, a fixed number of times it must be denied. It is not that any number of times it can be denied. So any solution you go for a critical section problem must have these three: mutual exclusion, progress, and bounded waiting. Is it understood, or anyone having doubt on these three? So now we'll go for finding the solution for this critical section problem, and that solution is known as the what? The solution known as the Peterson solution. Known as the Peterson solution. Okay. What is the solution is? This is a classic software-based solution to the critical section problem. Good algorithmic description of solving the problem. Peterson solution is restricted to two processes only. Do remember, this is important. What is the limitation of this Peterson solution? It is being, the Peterson solution is restricted to two processes that alternate execution between their critical section and the reminder section. So if you have two processes are there and they want to enter to the critical section, then this Peterson solution will work. This is not the only restriction. There is another restriction, is that assume that there is a load store machine language instruction are atomic. Atomic means the load operation or the store operation that is being done, it is done as a whole. It is a part of which cannot be done, right? So load and store machine instructions, machine language instructions are atomic in nature. So they cannot be divided. They cannot be interrupted between. So do remember, Peterson solution has two constraints over here. One is that it is only for two processes. Second is that the load and store machine instruction, if you are using, then these are atomic in nature. What is load? Load to the register or store from the register to the memory location. Okay. So suppose there are two processes, right? You have two processes that share two variables. One is turn, another is flag. Flag is a Boolean variable with an array of two. That means flag can store two items. Both can store only Boolean value, true or false. Try to understand. So flag of 0, flag of 1. So flag of 0 can have values what? True and false. Flag of 1 can have value true and false. So what are these two variables actually? The turn says that the variable turn indicates whose turn is to enter into the critical section. Who will enter next? That it will say turn. Suppose turn equals to I. This means what? The process PI is allowed to execute in its critical section. Is it understood? If there are two processes I and J. If I say turn equals to I, this means that process PI is allowed to execute in its critical section. If I say turn equals to J, that means PJ is allowed to execute in its critical section. So if I say flag of I equals to true, one variable is turn that I have already said. If flag of I equals to true, that means that PI is ready to enter in its critical. Ready to enter. That is what? Allowed to enter. This is ready to enter into the critical section. If flag of I equals to false, that means PI is not ready to enter into the critical section. Is the variables understood? Two variables, turn and flag. The turn is a variable of size 2. So it is a variable of size 2 actually. So this is somewhat like this. This is flag of 0 and flag of 1. This can store either true or false. Like that we can store. Correct? Now look here. So any process, whether it is process PI or PJ, any process wants to enter, what it will do? There are two processes we have already assumed. There are two processes P0 and P1. Because initially I have told Peterson solution is for two processes only. Suppose we have two processes P0 and P1. When presenting Pi, what is the value for Pj then? Pj is 1 minus I. If I is 0, 1 minus 0 is 1. If I is 1, then 1 minus 1 is 0. Is it understood? When presenting Pi, we use Pj to denote the other process. Pj to denote the other process. That means J is equal to 1 minus I. Is it clear? See, if I is 0, that means J is 1 minus 0 is 1. So two processes are being named I and J. So what is our requirement? Whatever the solution we may make, that solution should have those three requirements: mutual exclusion, progress, and bounded waiting. Just look into this algorithm. The algorithm says initially the flag is false for both. For both, it is false. So we have two locations over here. Both are false initially. Both are initially false. Correct? Now, suppose this is I and this is for J. This is for I and this is for J. Now what I'll do, for any process that wants to enter, it will make flag of I equals to true. It will make flag of I equals to true. So if suppose I wants to enter, it will make it true. It will make it true. And turn equals to J. So turn is actually another variable. turn is actually another variable. Suppose this is turn. Okay, so let this is turn. The turn equals to j. So we'll write j over here. That means the turn is j. The flag of I equals to true. Now, can you tell me whether the condition what is given in while loop is satisfied or not? And if it is satisfied, what it will do? Just look into this. Initially, both are false. This is flag actually. This is flag. This array that you have taken is flag. Flag of 0, flag of 1 that you have taken. Correct? So can you tell me that whether the while loop that you have given, the condition that you have given, this will turn to be true or false? This is true or false? Flag of j. So this is false. So look over here. If it is true, then what is given? Semicolon. That means it will just it will revolve over here only. Once it is false, it will get into the critical section. So once it is false, that means condition is false now. So process I will enter into the what? Into the critical section. So after executing in the critical section, while coming out, it will again make it false. It will again make it false. Is it understood? Now we'll see that how it will ensure that two processes cannot enter into the critical section. The same code is being used by both the processes. This is being used by both the processes, and we'll see that how this code ensures that no two processes can be there in the critical section itself. Let us go for two processes, P0 and P1. This is P0 is executing, P1 is executing. Both wants to enter into the critical section at the same time. Both wants to enter into the critical section at the same time. And here we'll take, both are what? Both are sharing? Both are sharing the flag. Both are sharing the flag. And as I said, initially this is false. This is false and this is false. And this variable is what? The flag variable. This is a flag variable. Then we have turn. Turn is another variable, right? This is the variable turn. Okay. So now let us, one of the process wants to execute. There are two variables are there. Flag is initialized to false. Turn is given. Two processes wants to enter the critical section. At a particular time, suppose P0 time, suppose P0 first try to execute in this critical section. So what will happen? The P0, this is code for P0, this is code for P1, right? Both this code actually, whoever the process wants to enter has to execute the code. What P0 will do? P0 will make it P0, the flag of 0, it will make it true. So it will flag of 0, it will make it true over here. It will make it true, correct? And turn equals to 1, so it will make it 1. Is that clear? Flag equals to true, flag of 0 equals to true, and turn equals to 1. Now the next is the condition. Condition is what? Flag of 1. The flag of 1 and turn of 1. Turn equals to 1. Whether what is flag of 1? Flag of 1 is false. So false and something is false. So it will enter into the critical section. Is it clear? Now who is there in the critical section? P0 has entered into the critical section. Do you agree or not? Do you agree or not? By executing this, P0 will be in the critical section or not?
Yes, sir.
Okay. Now, when P0 is in the critical section, P1 wants to enter into the critical section. Now we'll see whether P1 will be allowed to enter into the critical section or not. Whether P1 will be allowed to enter into the critical section or not. Okay. So now remember, now P0 is executing over here. Here the P0 is there. Whether our code is allowing the P1 to execute or not. Correct? P1 is there in the critical. Now, when P1 wants to execute, it will execute its own code. What it will make? It will make flag of 1 equals to true. So it will make this flag of 1 equals to true. Correct? Because this is shared by both the processes. It will make it true. Turn equals to 0. So it will make it what? It will make it 0. It will make it 0. Correct? Now look into this condition. Flag of 0. What is flag of 0? True or false? What is flag of 0?
True.
True. What is turn equals to 0? Is true or false?
True.
So if it is true, what to be done? It is semicolon. Semicolon means it will just wrap over here. It will just move over here. So it will not go inside. Rather, it is just moving over here in the while loop. It will go on checking again, like that. It will go on checking the condition. Is it understood? It will put in an infinite loop as long as the condition is true. Try to understand. It will be put in an infinite loop over there only. It is spinning over here. It is spinning over here as long as the condition is true. But in the first case, it is false. Therefore, it has entered. So P0 is entered into critical section, while P1 cannot be entered. P1 is there still in the, it's waiting over here, spinning over here, waiting for the lock. Spinning over here, waiting for the lock. That means waiting for, it should be, this condition should become false so that it can enter. But this is not happening. Both are true now. Suppose P0 has finished its execution. Let P0 has finished its execution. So while coming out, what it will make? Flag of I equals to false. Flag of I equals to false. So it will make it false. It will make the flag of I equals to false. Correct? The moment it makes the false, this becomes false. This condition will become false or not? Because flag of 0 is now false. So false and true is a false. So it will enter into the critical section. So P1 is executing in its critical section now. P1 is executing in its critical section. Is that clear? Suppose P1 is executing in its critical section. At the same time, P0 wants to enter. P1 is in the critical section. P0 wants to enter. So when P0 wants to enter, it will make this as true. It will make this as true. If flag of 0 is true, turn it will make it as 1. Now it will check what is flag of 1. Flag of 1 is true. Turn equals to 1 is true. So it cannot enter. It will just looping over here or spinning over here. So while P1 is in its critical section, P0 cannot enter into the critical section at the same time. Correct? The moment it comes out, it makes what? Flag of I equals to false. So it will make this as false. So if it will make this as false, then the flag of I equals to plus. What is I for P1? This is flag of 1. So it will make it false. So once it will make it false, this condition becomes false and it will enter into the critical section. Is it understood what I am saying? Is it understood?
Yes, sir.
Anybody having doubt on this slide? Anyone who can say which is the entry section? Which is the entry section?
While loop.
While loop is what, and what is the exit section?
Flag of I.
Flag of I equals to false. Correct? So here we have three sections over here. One is the critical section. We have this critical section. We have a entry section. In the entry section, it will do this. Before entering, it will do this. And while coming out, it must do this. Correct? For both the, actually this is one code I have written for both the processes. I have written for 2 times. Actually it's just the code, and this is your entry part. And this is your exit section. The reminder section is written. Is it understood? Now this is one of the solution for critical section problem. Now we'll check that whether it satisfies all these 3 conditions or not. What is the first condition? Is the mutual exclusion. Mutual exclusion means at a particular time only one process must be there in the critical section. Yes, it is true, it is there. Second, bounded waiting is progress. When it comes out, it allows the next process to continue. Bounded waiting, as there are 2 processes, so they don't have to wait for the indefinite period of time. Is it understood or any doubt? Anybody having doubt on this slide? Anyone having any problem? This is the Peterson solution for 2 processes only. So on a system with 1 CPU, Peterson's algorithm is guaranteed to work because program own behavior is observed in program order. But on systems with multiple number of CPUs, the algorithm may fail to work. To remember, the systems with multiple CPU, the algorithm may fail to work. Why it is there? Because the program order of events occurring on one CPU may not be perceived differently on another. Suppose the order in which the first CPU is working, the second CPU might work in some different order. So there is a chance that the algorithm may fail for multiple number of CPU. Correct? So that they may cause early entering into the critical section and early existing for the. So that occurs if you have multiple number of CPUs are there. Is that clear? Synchronization hardware part, I will just tell you that what is the synchronization hardware part. This I will discuss later. This is actually being left for you for self-study. Anyway, the synchronization hardware is a solution for the critical section problem. It says that you put a lock before entering into the critical section. While coming out, you release the lock. Before entering, you put a lock, and while coming out, you just release a lock. But for that, you have some complex operations required. And this part, actually, the synchronization hardware, we have left it for your self-study. I'll share you the slides. You'll read of your own. This one. We'll directly go to this. Critical section problem which with locks. So many systems provide hardware support for implementing the critical section code. Is actually by using the lock. They use the lock in synchronization hardware. So we'll now read a solution to the critical section problem by using the locks. What we will have over here? We have the critical section, right? What we have over here in this locks, this is suppose our critical section. This is our critical section. It says that we'll put a lock. Before entering into the critical section, we'll put a lock or acquire a lock. While coming out, we'll release the lock. This is the simplest solution it has given, that before critical section you put a lock, and while once you put a lock, that means no other process can enter into the critical section, and while coming out you release the lock, right? So we'll see that how this can be realized or how it can be possible. This can be the synchronization problem can be solved by using a tool called semaphore. Correct? Semaphore is very, very important. What is semaphore? Semaphore is a synchronization tool. Semaphore is a synchronization tool for solving the critical section problem. Semaphore is a synchronization tool for solving the critical section problem. Right? It is just a tool. So to overcome, so what difficulty we have in the hardware-based solutions? In the hardware-based solution to the critical section problem are complicated for application programmers to use. And that is the reason to overcome this difficulty, we use a synchronization tool called semaphore. Correct? If it will come, what is semaphore? What will say? Semaphore is a process synchronization tool for solving the critical section problem. Correct? And what is this semaphore is? The semaphore S is an integer variable. Semaphore S is an integer variable. So S can only be accessed via two indivisible operations. The S, do remember this, all these points are important. The semaphore S is an integer variable, first point. Second, it says S can be accessed via two indivisible operations. Indivisible operation means atomic operations. Atomic operations, they cannot be divided, either all or none. Either all instructions will execute or none of them are executed. It will be considered like that. You must have read in the transaction management in your database system, DBMS, you must have read about the consistency, or what is that called, atomic operations, acid properties. There, what is this atomicity says? What does this atomicity says? Anyone who can say atomicity property?
Sir, it says that either the process will be executed fully or no, or none of the including process will be executed.
Yes, correct. So either all statements of those will be executed or none of them, all or none. Right? They are not divisible, indivisible. Similarly, for that integer variable S, two operations will be carried out, P and V. Suppose two operations. There are two operations that can be carried out. And those two operations are indivisible, means we cannot execute a part of it. Either we will execute all or none. Is it clear now? S is a integer variable, we say is a semaphore. So semaphore is a integer variable. But it is not like any other ordinary variable. With ordinary variable, we can do any operation. It says that only two operations can be done. Only two operations. But those two operations are indivisible. Indivisible means atomic. A part of which cannot be done, either all or none. Is that clear? Now, these two operations are called wait and signal. Wait and signal. I repeat it again. A semaphore is an integer variable. With that integer variable, two operations can be performed. One is wait, second is a signal. The wait is also called P, signal is also called V. These P and V operations are atomic in nature. Why it is called P? Because it comes from a Dutch. Why it is called P and V? Because it comes from the Dutch word is about the to test or to increment. So this wait is called P and the signal is called the V operation. P and V operation. There are two operations that can be carried out on the semaphore. Right? Now, what is this P and V operations are? What are these P and V operations are? Look into this code. And do remember, this code will be always be used throughout our discussion. So it's better to remember this code. This is for wait, and this is for signal. Wait is called P operation and signal is called the V operation. The signal is called the V operation. See what it does. So it passed the semaphore to the wait function. Suppose the wait function I am doing. So pass the the semaphore into the wait operation. It checks while S is less than equals to 0. So initially S equals to 1. Initially this semaphore equals to 1. Correct? The semaphore is initialized to 1 initially. Now, suppose this is my critical section. This is my critical section. This is the critical section. Before critical section, let I execute the P, and while coming out, I execute the V. Not necessary that always P, first P, then V will be executed. This is an example I am taking. Simplest example. This is the critical section. Before critical section, I am executing P, and while coming out, I will execute V. What is my semaphore variable I initialized? S is 1. So it will come over here, weight of S. Weight of S means weight 1. So it will come over here. Weight 1, it will come over here. While S is less than equals to 0. Is it less than equals to 0? So S is not less than equals to 0. Right? Condition doesn't satisfy. So it will come out. So it will come out. Sorry, it will come out from this loop. It will make S minus minus. So it will make it 0. Try to understand what I am doing. S is initially 1. The condition doesn't satisfy in the while loop. If it will satisfy, it will be over here only. It will spin over here. As the condition doesn't satisfy, it will make it 0. It will make S as 0 and enter into the critical section. So I have executed the P or wait. Now I can enter into the critical section because I have executed this code. So I'll go to the critical section. Now think of, suppose the process is in the critical section, another process wants to enter. If another process wants to enter, he must also have to execute this P. So when it will start executing P, what will happen? Now what is the value of S? 0. So S less than equals to 0, it satisfies. So what, as it satisfies and the semicolon is given over here, so it is just spinning over here in this while loop. So as long as S is 0, it is just spinning in the while loop. So it is just spinning without doing any work. It's continuously checking the status of S. Correct? So it doesn't allow any other process to enter into the critical section. Similarly, while coming out, suppose the critical section work is over. While coming out, the process execute the V operation or the signal operation. What is the signal operation? It will make S plus plus. So signal will make it 1 again. It will make the semaphore to 1. So once it becomes 1, this condition becomes false. Once the condition becomes false, the process can enter into the critical section. By making it S minus minus, it will enter into the critical section. So what we are doing? Before the critical section, we execute that wait function, and while coming out, we execute the signal. Is it clear, or anyone having doubt for this wait and signal function? Wait and signal operation. These are two different operations.
Once again, signal operation.
Signal operation.
Once again, that signal operation.
Okay, okay. Okay. Suppose this is my semaphore variable s. The s is initialized to 1. Right? S is initialized to 1. This operation is indivisible, means a part of this cannot be executed. Either it will execute all or none. These are indivisible operation. Similarly, signal is also indivisible operation. The signal is also indivisible operation. That means a part of this cannot be executed. Correct? Now, this is my critical section. Multiple processes wants to enter into this critical section. Multiple processes wants to enter into the critical section. So before entering into the critical section, before coming over here, suppose I put the P operation. I put the P. They have to execute the P operation so that they can enter. Suppose they have to execute the P operation before they enter, and while coming out, they must have to execute the V operation. This is the condition that I have met. So suppose one process wants to enter. So now what is my S? S is 1. So 1 less than equals to 0. Is the condition true or false? S equals to 1. Condition is true or false? The condition is false. So if it is false, so it will come over here, because if it is true, it will remain over here, because semicolon I have given. So as it is false, it will come over here. It makes S minus minus, so it will make it 0. So it will make it 0. So now it will enter into the critical. P operation has executed, so it will enter into the critical section. Now my current value is 0. Now at the same time, another process wants to enter, whether it can enter or not. Whenever another process wants to enter, it will execute the P operation, because I have written that before critical section, P has to be executed. So P is in the entry section. So it will try to execute the wait. What is the value of S now? Value of S is 0. So while S less than equals to 0, the condition satisfies. So as the condition satisfies, it will remain over here. So it is spinning in this while loop. It cannot enter into this S minus minus. It will just spinning over here. Correct? So any of the process will come, it has to spinning over here. One process is there in the critical section. Only one process is there in the critical section. When that process has finished execution, it has finished its execution. So while coming out, it will execute the signal. Correct? So what is the value of S now? 0. So this is 0. 0 plus S plus plus. So it will make it what? It will make it 1. It will make it 1. And the process will come out. Now what is the value of S? S is 1. So S is 1 doesn't satisfy over here now. So the other process which is waiting now get into the condition is false. It will get into over here, make it 0. Make it 0 and enter into the critical section. This is something like, you must have observed that in a railway station, your platform is there, right? Your platform is there, and you have a green light, green or red light, an indicator is over there. Whenever a train wants to enter into a particular track in the railway station, it will look into that indicator. whether it is red or green. So if it is green, it will enter by making it red. Try to understand. So if it is 1, it will enter. So it will enter by making it 0. So it will enter by making the green light, by converting green light to red. Why it will change it to red? Because by changing it to red, what will happen? When the train enters, it will check for the light signal. If the signal is green, it will enter. But while entering, it will make it red. Why it will make it red?
So that no other train can enter.
So that no other train can enter into in the same track. Correct? So now it will remain in the track, in the same track for some time. After the operation is over, all its work is done. Now it will leave. But while leaving, it must allow the another train to come. So while going out, it will turn that or revert back that red to green again. So we do S++ here. We are giving a signal that the next process must come by incrementing the semaphore variable. By incrementing the semaphore variable. This is just a simulation of that. Those are being observed in the railway station. You have a green light, the train enters by changing it to red. And in the meantime, any train that comes, it will found it red. It continuously checking the status. It is continuously checking the status as long as it is red. So once it becomes green, it can enter into the. So how to make it green? The train which will left the critical section will turn it into green again. Correct? So this red light, the red light is a semaphore, actually is a variable, which has two operations. Either we make it green or red. So here we have two individual operations, wait and signal operations, and which can be done on a particular integer variable, on one integer variable. Just a second, one. I hope it is understood. Anyone having doubt on this slide? Is it clear, or anyone having doubt for this semaphore?
Yes.
Can anyone say that what is actually a semaphore is? What is a semaphore? Any one of you? What is a semaphore? Semaphore is a? What is a semaphore? Did you understand this, what I have explained or not?
Yes, sir.
Then you should define what is a semaphore is. I said semaphore is a synchronization tool for solving the critical section problem. It is an integer variable which has two indivisible operations, wait and signal. The question will come, what do you mean? What is a semaphore means? You have to write it is a synchronization tool for solving critical section problem. It is a integer variable which has two indivisible operations, wait and signal. This has to be written completely. I hope this slide is understood now. Okay, so there are actually two different types of semaphores. These variables, the integer variable that we take, there are actually two types of semaphore are there. One is called the binary semaphore, whereas the other one is called the counting semaphore. Right? The semaphores are of two types, binary semaphore and counting semaphore. The semaphore that we have discussed now was a binary semaphore, which has only two values, 0 and 1. Binary semaphore has the value 0, 1, 1. We have seen in the previous case, we have seen it has only 0 or 1. We are not incrementing it, either 0 or 1. So in binary semaphore, integer value ranges between 0 and 1. And it is initialized to what? 1. We have seen over here, what is our initialization? Initialization was 1. The initialization was 1. And this binary semaphore is also known as mutex. The binary semaphore is also known as the mutex lock. Mutex lock. Mutual exclusion. Mutex means mutual exclusion. Right? It is also known as mutex lock. This is used to deal with critical section problem for multiple processes. I hope it is understood. At least three things you have to remember. In binary semaphore value is 0, 1, 1. Binary semaphore value is 0, 1, 1. This is initial to 1. And these are called the mutex lock. This is called the mutex. Right? There is another kind of semaphore is called the counting semaphore. Counting semaphore. The counting semaphore integer value can range over unrestricted domain. So now this integer that you do not have a restriction of 0 and 1. You can go on counting the semaphore. So you can have the semaphore having 1, 2, 3, 4, 5, 6, 9, like that you can have values. So value can range over the unrestricted domain. Right? It is not 0 and 1. It can be any integer value. And this is used to control access to a given resource consisting of finite number of instances. So if you have finite number of instances, are there 5 number of hard disks, 2 number of tape drive, if you have a finite number of instances, this is used to control access to a given resource. So a resource may be requested by a number of instances. A resource may be may have a number of instances. So to control it, we may use the counting. We will have an example for the same. For the time being, you remember that counting semaphore has the range over an unrestricted domain. Unrestricted domain. This is initialized to the number of resources available. Each process that wishes to use a resource performs a wait operation on the semaphore by decrementing the count, and whenever a process releases a resource, performs a signal operation on semaphore by incrementing the count. Just look over here. Any process that wishes to use a resource, use what? By decrementing the count. By decrementing the count. If somebody releases, then it will have to increment the count. If you would have remembered that in signal and wait, in wait, what do you do? In wait, we decrement the semaphore. In signal, we increment the semaphore. See over here. In wait, we decrement the semaphore. In signal, we increment the semaphore. But this is only between the 0 and 1. But just think of, if the S can be 1, 2, 3, 4 like that, what will happen? Every time a process will enter, we will make it S minus minus. And every time a process go out, we will increment S plus plus. Right? So it is not only 0, 1, 1. You have a multiple processes will enter, it will make, suppose I have 15 resources, one resource is allocated, we will make it 14. Another resource allocated will make it 13. So every time one resource will be subtracted by decrementing the S. And when S becomes 0, it will wait. And while coming out, one resource has finished execution, so S is incremented, that means S is available. Is that understood with the counting semaphore and binary semaphore? Is that understood or not? I think it's time I will take the attendance. Roll number. Four, 5, 6, 7, 8, 12. 25, 7, 30, 32, 33, 34, 55. So the absent roll numbers are roll number 2, 22, 25, say 27, 30, 34, 37, 39, 45, 51, and 73.